Good morning, afternoon, or evening. Brin with Trained by Techs here today. Pretty excited about something that we found. In this case, it's going to be a short one. I know you guys probably don't believe me if you've seen any of my other videos, but I promise you it will be shorter. Anyways, today we're excited about something, but we wanted to share what we're working on real quick. This is a 2014 Chrysler Town & Country 3.6 liter. For those of you that are experienced and work on domestic lines and know this vehicle, know this engine, I probably can stop the video here. You know what's wrong with it, but that's not the point. In this case, we were able to use what we know in order to do some experimenting, which came up with some pretty cool results. Before I get too far, I want to make sure that I pay homage to those before me. Jim Kokonis, Richard Falco, and Hans Jorgensen. And the reason I bring up their names is because they have they've put some thought outside of the box. You know, you hear that all the time. It's pretty cliche, but in this case, it's absolutely 100% accurate. And they've helped me and others understand that we are our own limitations to what we can kind of do, especially when it comes to using, you know, test equipment for different things than what maybe they were developed for. In the case of Jim Kokonis and Richard Falco, they've been doing some really cool stuff with ultrasonic testing. You haven't seen anything official yet, but they have some material that I think you'll benefit from very soon, so keep your eye out for that. Very cool stuff. Hans Jorgensen did a video for us. You guys probably recall, many of you I know, where he used a pressure pulse sensor. He kind of combined it with a stethoscope and of course connect that to an oscilloscope to help him pinpoint noises. Now those kind of helped to influence me, and I wanted to make sure that I gave credit where credit's due there. So coming back to this Chrysler Town & Country, yes, we can come back to the experience that we may have with this 3.6 liter engine, and they're notorious for certain things, but that brings me to another point. When we're talking about diagnostic work or learning new testing techniques, we oftentimes, and I again paying homage to those before me, Jim Morton, Brandon Steckler are some of the ones you hear it the most from, or at least I have, but I often teach that as well now because I think it's absolutely true. It's very important that when you're learning new testing techniques that you practice on known good vehicles, because when you're working on broken cars, there's just more variables there, right? You don't know if what you're seeing is a good data, good scope capture, whatever, or if it's something that's showing up because the car is broken and it's related. So the other thing you can do, though, which is really cool, is if you know what's wrong with a vehicle, you can also use that experience too when learning new testing techniques. And that's what we've done here. What we know is common on these, so we've done some experimentation, which has been really cool, but because we kind of had an idea what to expect. So let me get to the point. On this 2014 Chrysler Town & Country, yes, we're dealing with an engine ticking noise. Now, drivability-wise, it seemed to be running pretty well, which those are very good clues. You know, if we're wanting to pinpoint the cause of the noise and we know the drivability is, that is running pretty well. If you have any experience with engine noises, that's obviously helpful. I have some, but it's not always been my strongest. That's not my strongest, asset, I guess, if you will. I certainly, there's room for improvement there. The biggest thing for me, it really is, because we're an all-make shop, sometimes you can expect, certain noises that may be traditional mean this, may not necessarily always mean that, depending on the engine designation. And if you don't have the familiarity with that, then that can be troublesome. But the biggest thing that I find is just pinpointing. When my head's under the hood, I think it might be this noise is coming from down low, and then I'm like, I don't know, I can't tell if it's down low or up high, which of course usually means different things. But the biggest part is just that, down low, up high, is it right bank, is it left bank? Depending on where you listen, it could sound like either, right? So that's kind of been my limitations, unfortunately, and I've worked through them, but this time we've done some really cool stuff to try to pinpoint it without having to rely on just these things. So very excited for what we found, and I appreciate you guys coming along. I think you'll enjoy what we were able to, our experimentation and what we were able to determine and actually pinpoint with our new, with our experiments. So thank you very much for joining us. Let's get to work. So I'll get to the point. As I mentioned in my video, Jim Kukunis and Richard Falco with CarQuest Technical Institute, they've done some really cool stuff with ultrasonic testing, and then being able to connect an ultrasonic tester to an oscilloscope to use for all kinds of diagnostic applications on vehicle systems. Really cool. But Hans Jorgensen connected a first look sensor to a stethoscope, and I don't even know if I've seen anybody do anything like this. I think I've heard conversations about it. But I decided I wanted to make, a device that we could pinpoint noises, but also connect to the oscilloscope so that we can visibly see them. Kind of like Hans did, but instead of using a pressure pulse sensor, using piezo technology, which is, of course, in this case, a knock sensor. Now, I think I set one of these aside from a job that we did where the knock sensor was good, but the harness that came with it was bad or something like that. I can't recall. But I planned on making the probe for the oscilloscope, but never did get around to it. Now, in this case, our good friend Carlos Mercado, which happens to work with us here at Assured Auto Works, he was more motivated than me, and as you can see, he actually made one. On this end here, of course, is a banana here, but in my case, I was using a Pico, of course, so we could just, all I had to do, actually with just a regular test lead at that end, we were able to get it done. So as far as just kind of talking about connection, you can do all kinds of different things, but this is what we ended up doing and connected it to a regular test lead, and it worked out really nicely. We're excited to show you the results, but yeah, basically a knock sensor that he just kind of configured in a way that he could use kind of as a stethoscope that he could connect to the oscilloscope. And we were able to use this in conjunction with something else, which we'll show you in just a moment, that was able to allow us to help pinpoint the cause of this ticking noise. Pretty cool stuff.
I know the point is really not to talk about diagnostic process, but I'd hate to do a video without kind of giving you some information to help certain folks. So, of course, checked for using the scan tool, we checked for fault codes to see if there was any misfire codes. And also we looked at misfire data to see if there's any evidence or information there that could help point us in the right direction. Not surprising, we didn't really find anything there because the engine was running pretty well. Next step, we did clear flood, which is, of course, depressing the accelerator pedal to the floor and cranking the engine over. Certain models will allow this, which is again called clear flood, but basically it disables the fuel injector so you can crank the engine over. The reason we would do this is listen to the rhythm of the engine as it's being cranked over. If there's a mechanical problem, there would be a consistent, generally speaking, there would be a consistent abnormality in the rhythm. The rhythm would change and it would be repetitive. That's not always the case, and the reason I say that is why we did this next test, which is a relative compression test. Relative compression test will use a high amp clamp and an oscilloscope to measure starter current, and by measuring starter current, we're able to, and displaying it over time like this, we're able to compare each cylinder to each other with regard to its ability to build compression or to build pressure in the cylinder. How do we do that? Basically, we're measuring the starter current. We know that each time a piston is going up in the cylinder during a compression stroke, the starter is going to work the hardest, so we know the starter current is going to be the highest at that point. So each one of these peaks would represent compression for each cylinder. Now, how do we determine which cylinder is which? That's why you see this blue trace. That's an ignition event. By using a second channel on the ignition event, we can determine which one of these starter currents represents compression for which cylinder. In this case, we use an ignition event for cylinder number 1, so we call this relative compression with sync. Synced ignition number 1, the ignition event should be really close to top dead center compression, which you can see it is. That's cylinder 1. We can count this out. Cylinder firing order is 1, 2, 3, 4, 5, 6, by the way. So 1, 2, 3, 4, 5, 6. Now, this is what I call trend or bird's eye view. Really hard to make decisions based off this, but even at this glance, you can see there's nothing obvious going on, but we want to get a little closer to get a little more analyzing a little better. When we get a little bit closer, again, we're looking for these to be pretty consistent, which would indicate that there's not obvious mechanical problem, at least causing a difference in compression. I do this test, you wouldn't think I wouldn't need to because the cranking cadence was good, but I have had personal experience where crank and cadence sounded pretty decent and found an anomaly during a relative compression capture that helped me diagnose a vehicle. So, but in this case, everything looks to be pretty good. These towers or these starter current peaks appear to be pretty close to each other. Nothing obvious anyway. So next, here's the meat of the story. Told you we're going to use Carlos's piezo sensor in conjunction with something else to help us pinpoint what's going on. In this case, we're using a pressure transducer in cylinder number 1 so that we can measure the pressure changes in cylinder number 1, and hopefully we'll pick up a noise. The engine ticking noise will show up using this probe in another channel, and we can compare the noise that we see on this channel to the pressure changes that are happening on channel number 1, which will have the pressure transducer again, cylinder number 1. So let's see what we have. Very important to do this bird's eye view or trend view as we did with this relative compression capture. It's very important to do this so that we can see if there are any anomalies, we can see that it's repeating and that it's consistent. So in this case, we'll talk about this. Red trace is the pressure transducer. I said channel 1 and 2, I think, on the previous slide. I want to make sure that you guys understand this is channel 2 and 3. I apologize for that. Channel 2, which is in the red trace here, is compression in cylinder number 1. Channel 3 is Carlos's piezo probe, and we're just touching that against the cylinder head as the engine idles, because this is not intermittent. This is happening all the time. It's ticking noise, and we can hear it at idle. Bird's eye or trend view, we can see this in the green trace. There is an anomaly, and it's consistent. There's a spike that's happening that we can see even at this glance, which isn't close enough to really make much, get much value in. So the next capture is this one here. This one here, we can see we have marked out. We've zoomed in a little bit closer for to analyze this better. We have 720 marked out in this compression capture, which is red. We won't be going over the details of what the squiggly lines mean in this video. I do have other videos that explain that. I know that I do. I'm sure I'm not the only Trained by Techs member that's done a video on this, but I know that I have done it. So you can find some of that information, and there's a lot of classes that are really good that cover this. But we do know that each one of these towers represents top dead center compression. And we know that this stroke here is going to be the expansion stroke. When we're analyzing it, that's what we call it. And we know when we see this pressure change here, that's when the exhaust valve open. And we know that this is the exhaust stroke, this is the intake stroke, and when we see this pressure change here during the compression stroke, which is this stroke again, when we see that pressure change, we know the intake valve closed. So really, for me, knowing where the exhaust valve open and the intake valve closed tells me a lot about what's happening here. But on the green trace, we're stoked because we see this repeatable noise that's occurring. And by marking up this waveform and sectioning it out into 4 strokes, we can see when the noise is occurring. In this case, let's move it. I guess before I get ahead of myself, I wanted to show you guys that we put the cursors up here and we locked them in at 720 degrees. And then we moved those cursors. Let me actually escape, and I'm going to show you on this live capture. Apologize, I meant to show you on a live capture. This is Pico 7. Goodness gracious. So at this point, same capture. You can see this repeating. We're actually going to kind of get a little bit more time on the screen. For those of you that are not used to Pico 7, anytime you're making a change from one to the other, it can be a little bit frustrating. Most of you are familiar with phase rulers. Pico 7, there's a toolbox over here to the left. You would turn them off or on. So we've turned them on. That's how you do that. And then partitions would be here. We're going to start off with 4. And anytime you want that toolbox to go away, you just click anywhere on the screen. So, goodness gracious. They do seem a little more difficult to move, to grab initially, but once you've got them, you're good. Again, those are the phase rulers, and I've got it partitioned 4 ways to show the 4 strokes. That's why you see this dark blue, light blue, dark blue, light blue here. What we're going to do is put our cursors, which those are in here as well. Graph rulers, you would hide them or show them. We're going to lock our cursors into the same place, basically, and open this rulers box so we can see we'll put it at 0 as opposed to trying to fight it, and we can do this and put that at 720 degrees. We know that's 720 crank degrees between the two, from one compression stroke to the next. We're going to lock that in, and the reason we're going to do that is you can see at a glance that these noise anomalies are happening every 720 degrees, but we won't want you to take our word for it. As you notice, I locked those. We know those represent 720 degrees, and I'm moving it and showing you that this noise is occurring every 720 degrees, which proves that it is, in fact, an engine mechanical noise that's coming through. And it's the only one. It is a 6-cylinder engine, so if it were other normal noise, then you would expect it to be more frequent, higher frequency than it is. You see this other anomaly is happening every 720 degrees as well. And there is a little bit of an anomaly after here, but right here, but you don't really see it here. So it's after, and you don't see it over here either. So that's an example of why you really need to put more time on the screen. Make sure that whatever anomaly you're looking at is repeatable, that it's a legit thing, that you're not wasting your time. So again, you can see this wider, larger, higher amplitude spike is 720 degrees, and this smaller one that's also repeating is also occurring every 720 degrees. Now we need to figure out what's happening when that noise occurs. So we're going to open this back up, we're going to unlock it, and now we're going to move this. We know when this change of pressure occurs here, that's when the exhaust valve is opening. So we can see this repeatable noise here appears to be happening when this exhaust valve is opening. We also know that this exhaust valve for the cylinder should close about 360 degrees, which if you see here, that is right in the middle, right about 360 degrees. So at this point, we're pretty confident that the noise that's showing up here, that's repeating, we know it's happening every 720 degrees, and we also know that it's happening when cylinder number 1's exhaust valve opens and cylinder number 1's exhaust valve closes. That's enough information to help us to go to the client and ask them to remove the valve cover on the bank 1 to do a visual inspection. But what if we had noise that was consistent like this happening every 720 degrees, but it wasn't lining up with any of the events that were happening here? In this case, I think it's important to go back. Let's go back to 4 partitions. It could have been the intake valve, right? Which we know happens about 360 degrees. But we also know it closes about here, and we're not seeing a consistent, repeatable noise pattern that's happening when the intake valve closes. But we are seeing when the exhaust valve opens and closes, so that's why we know it's an exhaust valve. But that's how we would know if it was an intake valve, if it were an intake valve, where we would expect to see it show up. Now let's move to 6 partitions, and if it were on a different cylinder, let's say exhaust valve had an issue on a different cylinder, then what we can do is we know this is where the exhaust valve would open on this cylinder here again, and we can lock those bad boys in. Well, that's close enough. 726 degrees, close enough. So we can lock those bad boys in. That would be where the exhaust valve were to open on this engine and then open again on its next cycle. And by having 6 partitions and putting those phase rulers where they are, we could also see where the exhaust valve opened on the other cylinders. If it were cylinder number 2, the noise would be here. Cylinder number 3, there may be a noise here. Cylinder number 4, when it opened, the noise would be here. But if it were making noise when it opened, we would expect there also to be noise when it closed. So if the noise was here when it opened, then we expect it to be the larger spike here when it closed. And that's how we would determine, you know, if the noise was repeatable on the green trace, but it wasn't lining up with the intake or exhaust valve open and closings on our cylinder that we referenced, in this case cylinder 1. That's how we would determine if it were on cylinder number 2 through 6. Just plotting out your phase rulers and partitioning them 6 ways for the exhaust valve open versus closed and intake valve open versus closed, and you would be able to determine what's going on. Pretty excited about it, but like I said just a moment ago, we at least have reason to pull the valve cover at this point to do a visual inspection, and that's what we did. So here is what we have. Exhaust valve cam lobe for cylinder number 1. And you can see I have 2 of the lobes here, so you can show you what good is versus what bad is. You can see there's heavy wear on the edges of this, and that's because this cast stamped rocker, the steel part of this rocker is rubbing against the cam lobe, and that's because this roller here has failed. So very cool stuff. We were excited to see it. What I would challenge you guys on, I told you early on in this case study that there was some clues as to, you know, just the fact that it was making ticking noise and not drivability wise it was okay, could be some clues as to what we're dealing with. And I'd like you guys to really put some thought into why we don't have drivability issues with this, and put them in the comments in the video. I think you know, I've put a lot of thought into myself, and I have a pretty good understanding of what's going on, but I think it's really cool to have you guys interact, so I want to see your comments as to tell us, you know, and kind of explain why you think that we have some noise but no drivability issues. So that's your homework.
Well, there you have it. I did tell you it would be shorter than my normal videos, which I think it is, but I think it's pretty cool. Again, we took something that we knew, a high failure rate on the 3.6 Chrysler engines, but we did some experimenting and testing that would help us not only on engines we know have higher failure rates, but other ones maybe, something that doesn't fail as often, and it'll help us to pinpoint the cause of the noise potentially. Obviously, we'll be needing to do a lot more experimenting to make sure this is something we can rely on, but my guess initially is that we can certainly get some pretty cool testing done using these testing techniques. So thank you again so much for joining us. Really enjoyed putting this together. It's been a while. I miss you guys. Look forward to seeing you guys soon on a live stream or something like that. So thank you so much for your time and attention. I hope you have an amazing week, day, month, year, whatever. Take care.